Any questions? Have you studied genus in some math course? Oh, you don't do topology or complex analysis?
Very complex analysis, but genus was not related.
Oh, I thought every math student will know that.
Maybe in some advanced analysis courses they go there. The basic DCs they didn't go there.
Because topology also has this pretty early, no?
The topology was not really a compulsory course.
Ah, see. Okay, so let's recall the last class. We mainly proved this theorem, which gives exact characterization of the degree of principal divisor of any function, any proper function in the function field. What is the zero part and what is the pole part, and it happens to be related to exactly the degree of a field extension, this finite, this algebraic extension. Any questions? And from this we learned that principal divisors, so basically for functions the zeros and the poles are equal in number, at least equal in degree, right, which is like a basic fact you would conjecture, but it's not very easy to prove for curves, because over curves your function is more complicated. It's defined only on the points of the curve. So your zeros and poles actually come from curves, and we are showing in this domain that even here the poles and the zeros are equal in degree. So that defines the class group. Div C and div 0 we can mod out by div A, which is the principal divisors. So we get the class group of divisor and the class group of degree 0 divisors, and we have an exact sequence of these abelian groups, CL0, CL and Z. Yeah, so now we will do something which is considered quite advanced. We'll talk about Riemann's proof of genus, and we haven't even defined what genus is. So this theorem will actually be the first definition of genus that you will see. So since you don't know what a genus is, let's first take a detour on genus. Right, genus is something that was invented to basically classify curves over the complex field. So what happens in the complex field? So in complex analysis, a curve C is drawn as a Riemann surface. So this in itself is an achievement, because if you imagine what is happening, you have this y square equal to, say you have a curve y square equal to fx, and if y and x both take complex values, it is not clear how will you draw this, right? You can only draw real points, you can't really draw complex points. So the complex axis generally you learn in school is, it comes with the real part and the imaginary part. So you have the real here and you have the imaginary axis as the y axis. So x has two axes and y also has two axes. So there happen to be 4 axis, right? So it's already a very high dimensional question in terms of real pictures. So Riemann actually gave a different picture for this, which is this. Okay, so he said that instead of 4 dimensions, we can actually imagine this in 3 dimensions. So what is done is that the x and y axis here are the real and the imaginary parts of your argument. So you can think of that. So this in particular is the map of y equal to, or y square equal to x. In our notation, this is y square equal to x, or in other words, y equal to square root x. So you are given a complex and you take square root, you get another complex, you get 2 options. So x is in the bottom plane, real imaginary parts, and then in the vertical axis is the real part of the answer, which is square root x. Okay, so the real part of square root x is what you are plotting in the vertical direction. There is obviously you are missing something here, which is the imaginary part of square root of x. So that part of y you are missing. So that is compensated by the coloring. So the colors actually are the imaginary parts, right? So this is what is called a Riemann surface representation of a complex curve. So you can see that this is not so easy to imagine if even after all this coloration. But at least Riemann defined this. You can now draw this. You can imagine in 3D space what. And the first thing you want to study is like, is this thing continuous? And next thing you study is whether this thing has holes. So are there places on this Riemann surface which the equation will not touch? So it will be a hole, right? So the number of holes is called genus.
So color is like a very representational thing. How is it a mathematical thing?
No, color is a spectrum. It's a real number, right? Colors from 0 to 1. So you can see that the red is not a single red. It starts from orange and it again ends in orange, and then it converts to yellow and green, and there are all these shades.
And basically, there are 2 axes only. Like color is also an axis in a way.
Color is also an axis, yes, but it is being colored inside the surface. So there are 2 things which are happening. First is a curve has become a surface because you want to visualize it in the real 3D space or real 4D space. So curve will become non-curve. So in this case, it has become a
goes to R, right? R and to R. Those are called surfaces, right?
Yes, surface is locally it will be a 2-dimensional object. So you will have you will have 2 tangents which are independent. So I mean basically a plane. In 3D, if you draw a plane, so here it's locally everywhere it's a plane, which is why you see these rectangles, and the rectangle has a color. So this color tells you what is the imaginary part of square root x, and the height of the rectangle from the base plane tells you the real part of square root of x. Yeah, so whenever somebody says Riemann surface representation of a curve, it is this. This is pretty nice looking because y square equal to x, if you remember, is birational to the line, right? So y square equal to x is actually the kind of the simplest curve you can think of because it's just a line in a way algebraically. So this is why the surface that you are seeing here, it will have no holes. I mean it will be continuous everywhere and differentiable in everything. So this is a genus 0 Riemann surface, and the complex curve is called genus 0. Yeah, so that's the picture, and then things will get crazy, which we will do now algebraically. So
one question, work is done to classify curves up to homeomorphisms?
complex curves, yeah, I mean, sure, you want to, I mean, even before homeomorphism, you just want to understand the difference between, as I said, y square equal to x and y square equal to x plus x cube. Right? Are these two things different? Now you know by our algebraic development that these two things are very different, because y square equal to x is just a projective line, but y square equal to x cube plus x. So let's write that down. So you want to understand what is the difference between these two, and you can as well put y equal to x also. So what is the difference between y equal to x, y square equal to x, and y square equal to x plus x cube? So the first two things are just the projective line, at least up to birational equivalence. The third thing is completely new. You can show that, I mean, you already have seen that these two are not birational. So geometrically, can you identify a difference? And believe it or not, the difference will be that in the last one there will be a hole, and in the first two there is no hole. And you can see that when you draw this Riemann surface over complex, which I will not do.
The first two things are spheres. Stereographic.
No, the first two things are what I just drew, right?
It's a sphere. It's S2.
Yeah.
You want something is
Yeah, but I don't want to say that, because here you don't see a sphere. Where is the sphere? So yeah, I mean, you are thinking in terms of homeomorphism, which we have not defined. So let's not do that. It's just a short detour. I don't want to detour into a course on complex analysis. So so yeah, that is the rough goal of Riemann and people before him.
So, like, are you trying to do like when two curves are not birational equivalent?
Yeah.
There always exists some hole. Like,
Yeah, exactly.
that is the exact meaning of it.
Yeah. There will always be a hole, and the hole basically signifies that. Yeah, so it is actually not clear what it signifies right now. In the picture, you will see it. In the 3D space, you will see that there will be discoloration, a part where there will be no colors because that part doesn't exist on the surface. But can it be measured and can it be computed? So we will formalize that. In fact,
Reverse implication. If two curves are birational, they should have the same genus. But then is the converse.
no, hold on. We have not defined genus, so we have just defined that picture. And the difference in those pictures between y square equal to x and y square equal to x plus x cube will be that there will be a place where there will be no colors. That place will not exist on the Riemann surface. Let's just hold on to that thought. So that part will be called a hole, naturally. So a hole is characterized how? So by drawing loops. Right, that is the first semi-formal description of a hole. So you have this continuous, I mean, almost everywhere continuous Riemann surface. So you start drawing loops around these rectangles, and if everything inside the loop is present, then it isn't a hole. And if there is some loop that you can draw inside which space is empty, then that's a hole, right? So kind of number of such empty loops will be called number of holes. That is the genus. But to really formalize it, you have to show that basically you have to use this equivalence of loops. So two loops are considered equal or equivalent if there is a nice transformation from one to the other. So this nice transformation is what Deeptajit was saying. There is a homeomorphism. I mean, it's basically, it should be an invertible transformation that takes you from one loop to the second loop and also back. Sorry?
Homotopy.
Yeah, homotopy. Yeah. So in the category of loops, it's an isomorphism. So this is, for example, loop 1, this is loop 2, this is loop 3. And by transformation, what is meant is that somehow you can map every point on loop 1 to loop 2 and every point on loop 3 to loop 1. Right? So in this sense, you can go back, you can transport from loop 1, 2, 3 in any way you want. So then all these loops are the same loop. So moreover, if there is a loop which collapses to a point, then it's a no loop. And this will only be possible if everything inside the loop is present on the surface, right? If everything is present on the Riemann surface, then you can keep shrinking the loop all the way to the origin, to the center, right? So it will become an infinitesimally small loop. So we say that there is no loop. That's the zero genus case.
It's a lot like a localization.
Yeah, of course. Yeah. So these things came first, and whatever we have seen in 2 months came last. But we don't want to keep doing this translation because it's confusing, at least for me, and also very painful. You have to define things here. You have to define what we have defined in the course, and then you have to show that they are equivalent. It's not very easy. So, yeah, so that is what is meant by nice transformation.
Modeled by you, right? Points. From point, take all function f by g, then over you make that equivalence class.
Uh,
All you can equivalent, all open sets in a way.
So for example, this loop 4 is just a point, and here loop 1 and loop 2 and loop 3 are the same. Okay. So we count this as 0 loop, and this we count as 1 loop. I mean, okay, I should not say 1 loop. Maybe this also converts into 4 and 4 shrinks to a point. So whenever some loop can be transformed into an infinitesimal loop as much as you want, then we say that essentially there is no loop, and we call that genus 0. Otherwise, genus is number of loops, actual loops. So genus of a curve is defined geometrically as the number of distinct loop classes. Okay, so this is the genus 0 case. So if everything inside is present, then you can shrink it to 0 loop, which is genus 0. If this happens everywhere on the Riemann surface, and if there is a hole, like this is a hole, and this is a hole, right? So then it means that genus is greater than 0. Right, so in particular, genus will always be a non-negative integer, and it will fit perfectly with our geometric intuition of what a hole is on a surface. Okay.
Why don't we expect like genus to be equivalent to the number of poles?
Yeah, so but pole of what? There is no global function
Okay.
except the equation of the surface, like y square equal to x. Uh, but yeah, I mean, you cannot really say that y square equal to x has a pole, because that is kind of the defining object. So it has no pole, it has only zeros. So you have to look at some other function. So that was the starting point of Riemann's theorem, that is there a magical function whose poles or whose zeros can tell you about the whole, right? So what you are asking is also what Riemann asked, and he could completely solve it actually. That is what we'll see. Maybe one more picture you deserve, which is quite a famous picture of a torus.
You want to say it's the genus is actually the number of poles as opposed to the number of loop classes. Because here you will get two classes, but the genus is
Where?
in the torus.
Yeah, maybe -1. Yeah, depends on whether you are counting the zero loop or not. I didn't want to count it.
No, here also you will not count it. You will get two classes.
Yeah, so
all of
maybe,
which are zero.
yeah, let's say -1. Fine. So there is a zero loop, there is a one loop, and there are many one loops. So the count is distinct loop classes -1, and this is also the number of holes.
Yeah. There is a constant.
Yeah, so this is another example. This is your first example of genus 1. So the blue part, you should think of it as a donut, right? So it's basically a cylinder which you have joined the endpoints, right? So it's basically a ring, a 3D ring. So in that you have only two kinds of loops. One is a loop which you can wrap around the ring, and the other loop is which you can which the ring is essentially the circle, right? So the orange one is the bigger circle of the ring, and the red one is the thin circle of the ring. Any third loop can be collapsed to one of these. Now the red one can be collapsed to a point, so it's a zero loop because everything inside it is present. The orange one is very different because ultimately it gets trapped, gets stopped by the hole.
So that should be distinct loop classes by 2, I think, not -1.
So this is a genus 1 object. Okay, which means that the number of holes is 1. Okay, so this is how it is defined in when you are doing actual geometry or when you are doing algebraic topology. This is the way you will understand. Well, you can first see the hole in the Riemann surface, and then to generalize it, you can study it via loops. Is that clear? So that's a short detour. Now the central question is,
Saying that the formula should be distinct loop classes by 2, because for one hole you are getting 2 loop classes.
why?
You have one loop class like this and another loop class like wrapping around.
Are you talking about red and orange?
The blue one? Yes. Yes.
Yeah, so in that, orange is the only one which is the hole.
Yeah, but in that surface you will get 2 loop classes, right? 2.
Yeah, so the genus will be 2 minus 1.
But in case of 2 holes, how many loop classes you will get?
You should get,
You will get one going around one hole,
should get
one going around the other hole, and one going around both holes, and the constant one. So you might be right. You get 4 different patterns.
Those going around two holes will be the same, right? Even the individual holes.
No, they are not the same.
Going around
because
different holes, they
you can
can't be the same because you can't shrink one into the other. They're going around different holes.
okay, that's problematic. So you are saying one around this, and another one around this, and other ones are silly, these ones. So you have distinct loop classes. So the answer is what?
The genus is 2, but the number of classes are 4.
So
I mean,
it's a
I mean,
three.
who is to n, right? We had that one is then you can choose any all k holes.
Mhm.
Figure out like 2 is to n, right?
Then it's 2 raised to n, yeah. Okay. So let me not go into that kind of a formula.
We had 1 and 3 equivalent, right? So even also
Yeah.
these two should be equal.
Where?
Loop 1 and loop 3 were equivalent, right? And they were different also. Like the individual ones should be equivalent here as well.
No, these are not equivalent. These are two different holes. How will you?
I mean, mapping could exist.
Oh. No, that will not be. I don't think. No. Yeah, I think you are. Yeah, we are confusing with the 1 to 3 example, maybe. Hmm. Yeah, that example may not be very good. So genus ultimately should just count the number of holes, because this we all agree. If when seen in the Riemann surface representation, the only way to imagine a complex curve. So in that the number of holes should be genus, and so we are getting that. So either there is no hole, which means that there is only one loop class, or there is one hole in the case of torus, that's genus 1, or this example. So yeah, so you can think about this. This is a whole area in itself, which will not touch in this course. But what we want to question now, which is Riemann's basic question, is do functions Kc, the function field of the curve, do functions Kc know about the genus? Right. So once you have defined this geometrically, genus, the question is whether algebraically the algebraic objects, the biggest objects you have are these rational functions defined on the curve. Can they tell you anything about the genus? Right. That is Riemann's question. With an incredible answer. So the LD sheaf that we have defined, Riemann showed that sheaf actually knows about the genus. So LD minus DD, difference between the L dimension and the degree, that exactly gives you genus. So Riemann showed this in an important year, that this LD minus DD minus 1 is equal to minus of genus. Okay. So this connects the geometric definition of genus with the algebraic object, which is the dimension of L.
There should be an inequality.
That is true. So minimum of this. So if you minimize this L minus D difference, you get the genus. Now we are not in the complex case, we are in the case of finite fields, right? So finite fields, there is no known representation, we cannot draw anything, so we cannot define genus, there is no geometric definition of genus. So what we will do is we will just cheat and we will take this as the definition of genus.
No, sure. LD minus GD can go to be very, very small also, right? Like can go
It-
to minus infinite. Like,
But it does not. So Riemann showed that it gets stuck in genus. You cannot go to minus g minus 1. Yeah, that was the brilliant insight of Riemann, and it is completely unexpected. I don't know whether there is any good intuition for that. Why was this done? But for him it was a theorem. So he wanted to actually, you can think of this as a way to compute the genus. He wanted, without drawing anything, he wanted to compute the genus, so it has to be an algebraic thing. So the algebraic thing is LD minus DD. So that is something you can actually compute. So it's kind of a optimization algorithm which will give you genus, right? And we will actually take this as the definition of genus because we don't have any other alternative for genus. So this left hand side becomes the definition. But for that we have to show that in our world also the minimum exists, right? Maybe the minimum doesn't exist. For complex curves he has shown it exists, and in fact it's equal to minus genus, but in our case it may not be true.
So it's almost like L of t grows linearly with after for large enough.
It's almost equal. Yeah, for low genus these two things are almost equal. So for example, when genus is 0, then you would expect that for your, let's say, random divisors, LD and DD will be very much the same. And as the genus increases, there are more holes. So this LD sheaves actually starts behaving in a wild way.
But
Okay.
the difference is a constant almost. L of d minus.
Yeah, for random Ds. I mean, it is not true for every D, but
For of large enough d.
of large enough degree, exactly. So for random D, you would expect this to be an equality. So
Can anyone compute genus algorithmically?
well, by the end of our proof, we will compute it. So since we'll compute it over finite fields, even. So since we don't have any way to define genus, over finite fields, we intend to take this theorem, which we haven't proved yet, as a definition. Okay, so the theorem will be now this. So there exists a number G, which we will call G for the curve over. So curve for us is always a transcendence degree 1 function field, right? So that is what is given to you over a base field small k. It can be anything. So there will be this number such that for all proper rational functions x, minimum over all m okay. So this will be actually even more specialized, even more a stronger thing than what I said before. If you just take a rational function and look at its powers and the poles, okay, so the L dimension of that -1 minus the degree of that, this is equal to minus g. It's lower bounded. That is what we'll show. And this is what this number exists, we call it genus. The genus of K. And the other part is that for any divisor LD minus 1 minus DD is greater than equal to minus G. So basically the second part is that this minima is independent of the divisor. So you can actually, so here we are only going, the minima is only over the integers m. Actually
So this theorem is for complex, right? K is for complex.
this should just be, I think, I don't need negative integers. I think natural should be enough. Yeah, sorry.
Theorem is only for complex, right? K.
This theorem? No, small k is our base field. Yeah.
You can't prove it for the finite field case also.
No. Riemann, in those days they did not have finite fields. They would only think about the field of complex, which is why I showed you that picture of Riemann.
Like theorem proved by Riemann, that's why I said finite field.
Well, because the proof is,
Who is work for general?
no, look at the first red part. Riemann showed this for complex curves, for his surfaces.
So then
Because he had a definition of genus already, which is by holes.
Okay.
Now we don't have a definition of genus, but we will just go through his proof, and this minima that we will get, we'll call it genus.
So it's basically showing that minimum exists here.
Yeah, the minima is a number, and that number for us is genus, because we don't have any other option for definition of genus. So actually we are in a completely hypothetical world. We cannot see holes, we cannot even define them. So whatever algebra gives us, we'll just call that genus. And we'll hope that everything works just as fine, which it will. So it will be more, it's an abstraction of Riemann's proof. Any questions? So actually what we have seen now, the proof is quite easy. We have already done the development, so just recall the degree proof that we did in the last class. We'll just refer to it. So begin with some proper function on the curve and think of the finite field case. So it will be a stronger proof than Riemann. As in the previous class, begin is the degree of the field extension, and let S be big enough. Which we also did in the last class. Remember, we had this for big K, we have a basis, and then for the basis yj, we had valuations and we wanted S to be big enough according to those valuations. So it's the same S as in the last class. And so from the last class, we know from that proof that for all t, what we had got is n times t is less than equal to L x to the s plus t poles, its L dimension. We had shown that ultimately the L dimension of the pole part of x to the s plus t is lower bounded by big N, which is kind of a constant. It's an absolute constant for us in the setting, times t. So as you exponentiate x more and more, the L dimension is increasing in a linear way, right? This is what this is saying. We got this in the last proof. This here. So L x s plus t is at least size of B, and we actually gave you this these B many elements also. So we are at that part of the proof, and yeah, so let's continue from there. So writing m equal to s plus t, we deduce that for all m at least s, let's check the difference L minus d. So this difference is at least nt from the above minus what is degree? Degree we have shown is m times the degree of x infinity, which is big N. So that's minus Sn. Right, so that is the proof of genus or of the lower bound. So as m is increasing, the L minus d difference remains lower bounded by s times n, both of which are independent of m. Okay, so irrespective of how high a divisor you take, L minus d difference will not get small. It will always be lower bounded by this absolute constant in our setting, s times n. So this implies that the integer mu x minimum of m this integer exists. Okay, so we can call this, we basically will just define this to be 1 minus g, and that g will call the genus. So that's first part of the theorem. Any questions? All we have done is we have shown that the L dimension grows almost linearly, it grows very fast in compared to the degree. So the difference between L and the degree cannot drop beyond a point. There is an absolute threshold which it can't cross, and that threshold is called genus.
Does this S depend on X?
Yeah, so that's the second part. Yeah, right now it does. So let's do the second part now. That genus doesn't depend on anything except your curve. Yeah, so that will complete the geometric intuition also. But before that, maybe I can say one thing, because it will be useful for computation. So note that well, n is the degree of the extension. So intuitively, if you had a function like f of x comma y equal to 0 for the curve, if that was the description of the curve of degree d, then this big N will be less than equal to degree of the curve, and S was, so you have to recall what S was, right? This was the valuation of essentially the conjugates of y. So that also will be upper bounded by degree. So which means that the genus is upper bounded by degree square. Okay, so the genus is not too big. I mean, this number, this proof also tells you that genus is only quadratic in the degree of the curve. Okay, so it's not that this can be exponentially large. So a curve cannot have too many holes. It depends only on the degree in a polynomial way. So you can potentially write down an algorithm for this.
It is degree d of x, right?
Degree,
D of x.
well, I meant degree of the curve. So I haven't defined it properly, but an example is if your curve is fx comma y equal to 0, then kind of degree of this polynomial. Okay, so I mean, a curve can be given to you in a very complicated way, but the curves which you will imagine first are these planar curves embedded in a plane. So they are given by a single equation. So whatever is the degree of that, you can see that big N is bounded by that, and S is also bounded by that. So the genus is bounded by quadratic in the degree. Okay, so it's a small number. It's not a very big number. Okay, so now let us do the second part of the theorem, which is that you can also minimize over all possible divisors and get the same genus. You don't need to work just with x infinity, it can be any divisor. So let's prove that. So yeah, so let's write down in its zeros and pole part. Right, so we separate into zeros and poles. The divisors are d0, d infinity, they are both positive. So which in particular means that D0 is greater than at least D. So what we will do is we will connect.
So D should not div A, right? Because 0 and poles are defined for principal divisors.
Yeah, but you can write any divisor into difference of positive.
D0 and belongs
No, no. So the definition of D0 is through D. You can write any divisor into positive and negative parts. Positive part is D0, negative part is D infinity. Yeah, yeah. So it's not X0, it's now a general D0. I just care about their positivity. So, so what I want to do is I want to study LD minus degree of D, and I want to show that this is again lower bounded by genus. So for that, yeah, so you are correct. Now somehow we have to connect this thing with x infinity because our first part is from x infinity. So we'll do it in two steps. We'll first connect D with D0. So since D0 is at least D, what you deduce is that L of D minus D of D is at least L of D0 minus D of D0. That's from the LD sheaf that we have studied. If you increase the divisor, then the difference can only get smaller. And from this I can deduce, well, okay, the other connection is from here. Connection to x infinity. So x m infinity right, since D0 is positive, I can also connect, I mean I have this inequality trivially, and I can now look at the L sheaf of this, of LHS and RHS. So what does that give me? This gives me that L of minus D0 plus minus D of that is at least minus D of xm infinity, right, which is which we have shown in the first part is lower bounded by 1 minus g. Yeah, so these are the two connections, and now let's combine this. Actually, sorry, maybe I should no, it's okay. I think G we have already defined, so it's fine.
So it means do it with gx and mu x.
I think mu, yeah, maybe mu x. Yes, you are right. This integer, yeah, maybe mu x is a better term here. That depends on x. Stay with mu x. Okay. So that's equal to, so degree of d minus dd0 minus degree of d0 plus degree of x infinity m xm infinity plus mu x, which is what? degree of xm infinity was that we know exactly, that's mn. Yeah, and m is arbitrarily growing, while d0 has been fixed for the discussion. So since m continues to grow, at some point this is positive. So the L dimension of minus d0 plus xm infinity is positive. That's what we have learnt from this. Okay. Yeah, so which means that there is a z, there is a function that exists, right? The L dimension is positive, so there is a function. In the L sheaf such that the definition of L sheaf, so by that you will get this essentially z divisor of z minus d0 plus xm infinity has to be non-negative, greater than or equal to 0. So we have rearranged that. Okay, and what do we learn from this? So we again use the L minus degree difference of both these sides to deduce that this is at least L minus d of xm infinity, which is at least mu x. Is that clear? So all I have done is I have now again looked, since xm infinity is a bigger divisor, so L minus d for that will be less than equal to of L minus d of the RHS. Now you just have to observe one thing here, that L of d0 minus z is the same as L of d0. Do you agree with that? So the
vector spaces may not be the same, but the dimensions are the same.
Yeah, the dimension of the L sheaf, it doesn't change if you add a principal divisor. Do you see this?
Yeah.
Maybe we write this down.
Because the inequality won't change.
Yeah, so L of d0 is the same vector isomorphic to L of d0 minus z. What is the isomorphism?
Multiply by multiply each function by
Yeah, so if you have a function here if you have a function f such that f plus d0 is greater than or equal to 0, then you have to construct a function g such that g plus d0 minus z is greater than or equal to 0. So for that you just use f by z, fz. That's the isomorphism. Okay. So up to principal divisors, L sheaf is nicely behaved and degree is also well behaved. So that is what I have done here. So I have written L minus d is at least L minus d of xm infinity. And yeah, so now you connect the two and you will get what we wanted. So now we have L of D minus D of D is greater than equal to mu x. That was the second part of Riemann's theorem. That for any divisor, so you define mu x via some fixed proper function x, but it also the lower bound also is satisfied by any other divisor.
Sir, can I go back a little?
Yes.
Like we show that the degree 0 means that vector space has some dimension. So we know there is some divisor in L minus d naught plus xm infinity, right? How do you
There
know-
is a z. Uh-huh.
But how do you know this principal divisor?
No. There is z is a function. L sheaf has functions. These are functions on the curve.
Oh, relation is collection of
Yeah.
divisors.
Correct. So I just wanted a function such that I mean essentially xm infinity and d0 should kind of be replaceable, and so they become replaceable if if the difference is only by a principal divisor, because on principal divisor both L and degree are well behaved. So that is what I have achieved. So immediately I have a connection with mu x now, and since I have a connection of d0 with mu x, I have a connection of big D with mu x, and big D was a general arbitrary divisor. So actually this genus that we have defined, every divisor satisfies this lower bound. Yes, so this actually means that mu x is independent of x. So it only depends on the curve and basically, which means the function field, transcendence degree 1 function field and small k. So what is the curve that you have drawn and what is the base field that you are studying? So as these two things will change, the genus may change, and it will change. But it doesn't matter what function. So this is an amazing proof or even statement of Riemann, because it's kind of controls all the functions which are defined on the curve. Okay, so genus becomes a canonical property of the curve. It doesn't depend on specific functions. So yeah, of course we will take small k to be algebraically closed. So for algebraically closed small k, which means it's equal to k bar, genus of k is called the arithmetic genus. So for a transcendence degree 1 function field, or for the equivalent analogous smooth projective curve C, the arithmetic genus is when you are over Fp bar. Is that clear? Yeah, and if you are curious, then you should that part is obvious. Yeah, so the way we have defined it, of course, for standard notion of genus in geometry for complex curves, it exactly matches this. That's clear by construction, by definition. So all these other definitions which you have that existed before, say in complex curves, they are all equal to this. So all the classical definitions are there, are consistent with this. Okay. Yeah, so that is the story of genus. Any questions? Yeah, Deeptujit was interested in an algorithm.
For that, you just take a divisor of larger than degree, and then you will get everything should become constant. L of d minus d of d should become constant.
So Riemann's proof gives an algorithm to compute genus. So what, I mean, I'll just give a sketch. So the simplest case, which is also used in computer science a lot, is this case of y square equal to fx over fp. So this is called a hyperelliptic curve. So for hyperelliptic, yeah, this is not a very good example for genus, but anyways, you will see the algorithm and then you can try to generalize it. So the basic idea in this case will be you have to compute the LD sheaf, right? That is the key object in Riemann's proof. So you first compute L of x m infinity. So if you have computed L dimension of xm infinity where x is the same x, then you know that for not very big m being some d square, where d is the degree of this polynomial f, the L minus d difference will become genus, right? And so degree is easy to compute of x to the m. So you just have to compute the L sheaf. So what is that? So this is equal to functions in this on this curve, sorry, not this f, let's make it capital F. So function small f such that the principal divisor plus this is greater than or equal to 0. So you essentially have to compute, you know that this is a vector space, so you have to compute a basis of this. So I'll make just two observations. First is that xm infinity is very easy to compute. I mean, whatever be the curve representation, this is, you just have to compute the zeros, actually the poles of x to the m, which will be very simple, right? It is just, in this case, the only pole is pointed infinity. Yeah, pointed infinity, yes. The 0 is just x equal to 0, and the pole is just pointed infinity. Yeah, so there, and then when you raise it to m, all you are doing is you are increasing the multiplicity of this pool. So it's very easy to compute this divisor. I mean, you explicitly know it. How easy is it to compute small f? So small f you can write like this. It's a rational function. So you write it as ax plus y bx cx plus y dx for unknown polynomials. Okay, any rational function, the degree of y can be reduced to 1 because y square is equal to big Fx. So whenever you see y square, you replace it by that. So your rational function in general looks like this. You just have to find ABCD. So you already know xm infinity, what are the points which appear there. You just plug that in this representation and you will get a linear system in ABCD. We get a basis. Okay, so you can get the basis in that way, solving a linear system. It won't be a very big system because you know that, I mean, you know an upper bound on the L dimension. It's not that large. So the matrices which you are using in your algorithm, they are not too big. Okay, so you can solve the linear system, you can find the basis, so you can find the L dimension, so you can find the genus. This is you can generalize it fairly quickly for any curve.
What is the bound in M?
Yeah, M that will come from the proof. No, it's only
We know about genus G and S only. N, S and G, but we don't know about M.
yeah.
T is a free parameter.
So that was in that you have to guess that it can't be too bad. Basically S plus T. It comes from here. This is the key equation. This last equation, we said that let T tend to infinity. But of course, in an algorithm, we never do that. We'll just make T big enough so that the next inequality, which is this, can be reduced.
How big can this be?
Yeah, but that you just pick T to be, say, bigger than Lx infinity. Because you are only working with integers here. So if you make the other part fractional, right? So basically, if you are saying that something is less than equal to 2 plus half, then it has to be 2 or less. So just use that. So these things can be worked out. I mean, you have bounds for everything. It's pretty small. And S plus T gives you the M. So yeah, so I don't think there will be any serious issue. It should converge very fast to genus.
Maybe we need to already know rocks part of the theorem, the canonical divisor.
For this?
Yeah.
No. I'll be surprised. This is a full proof. Yeah, so okay, details are missing, but it's not that surprising that you can bound everything here. The proof is pretty, I mean, it is as explicit as it gets. Everything is in terms of degree and all that of the field extension. Okay, so what will we do next? let's put this on record that genus is always non-negative. Why is that? Remember that we don't have a concept of holes, so this is not trivial, right? We have just defined mu x to be an integer. It can be negative, it can be minus 10. So why can't genus be minus 10? How do you show that? So we have shown that LD minus DD is always at least 1 minus G. So take D to be 0. Right, so degree is 0 and L is 1, so you get 1 greater than or equal to 1 minus G. So you get that G is non-negative integer. Okay. So genus will not be anything surprising. It will be a positive number except when it is 0. So you can still imagine the same kind of whole interpretation that was there in complex analysis. It's counting something. Now the other one unsatisfactory part of the proof is that it's an inequality, right? Mathematicians and pure mathematicians especially, they love equalities. So they would want LD minus DD to be equal to 1 minus G. But you can actually show that that is false. You can always find divisors such that left hand side is strictly bigger than 1 minus genus. So what is the hidden equality here? Okay, that will be our next lecture. So the degree of speciality of a divisor D is defined as delta D, which is LD minus DD plus G minus 1, which by Riemann's theorem is greater than or equal to 0. So can we interpret this degree of speciality and can we characterize it completely? So that when it is not 0, 0 would be the ideal case. When it is not 0, when it is positive, why is it positive? So what is special about the divisor? Why is it far away from genus? So how is delta D related? So how does delta D change with D? So sometimes it is 0. I mean, you know that at least once it is 0. Other times it is positive. So why is it positive? So this was answered in an exact way by Gustav Rock few years after Riemann. He was Riemann's student. Yeah, next what we'll prove is what is called the Riemann-Roch theorem. So Riemann-Roch theorem will be this the most beautiful thing you can expect. It will be an equality where delta D will be replaced by some canonical object of the curve, and it will tell you how the degree of speciality is changing with the divisor. And this canonical object that it will define is called a canonical divisor. Okay, but it'll need more abstraction, so we'll start it tomorrow. Rock actually died very early, but this is the theorem for which he is extremely famous.
So Riemann also died very early.
And Riemann died few months before Rock. So Riemann died and a few months after Rock died, but Rock was only 26 years old.